Hello everyone, I am Dileepa Marasinghe and I am presenting our work on LiDAR-aided wireless networks beam prediction for 5G. My co-authors are Nalin Jayavira and Nandana Rajatheva from Center for Wireless Communication, University of Oulu, Finland, and Sami Hakola, Timo Koskela, Oskari Tervo, Juha Karjalainen, Tiirola, and Jari Hulkkonen from Nokia Standards Oulu. We know exploring these higher frequency bands in 5G like millimeter wave and terahertz, uh, the connections are principally beam-based to overcome the propagation challenges in these bands. Therefore, 5G defines beam management procedures to ensure reliable connections, but at the expense of periodic measurement reports. Also, there's a recent interest in using sensing technologies with the wireless network, such as radar, LiDAR, and camera, which can provide situational information of the communication area we are operating in, which can be used to generate proactive decisions in the network and to monitor the situation. So in this work, we utilize an infrastructure mounted light detection and ranging sensor system or LiDAR system, which is simultaneously operating with the 5G wireless system. And we use the sensing data and the beam data from the wireless system to predict future beam decisions. Here I present you a brief summary on the 5G beam management procedures. So when the UE is not connected and trying to connect to the network, the access point transmits SSB beams, which are used by the UE to gain the initial access to the network. And when the UE is transferred to the connected state, refining the served beam pair to a narrow beam pair is done using the CSIRS beams. So once such a refined beam pair which are narrow is identified, the beam management procedure try to maintain this beam alignment when if the user is moving or if there is any blockage or anything through sending periodic beam measurement reports. In case of a beam misalignment due to mobility or some blockage, a new beam pair to correct the beam misalignment is identified. Therefore, this periodic beam measurement reporting is essential to maintain the link quality in the system since we are in the higher frequency bands. As I mentioned earlier, sensing technologies has gained a recent interest in the wireless communication community to help in the communication system. So these sensing technologies can facilitate positioning and tracking of the users carrying the UE, and this information can be used to predict the movement trajectory of the users or incoming blockages or loss and loss transitions, etc. Also, 3GPP has shown interest making a new study item to how to incorporate sensing to provide new services and enhancements to the communication system. And also there is work going on to uh, add artificial intelligence and machine learning for the new radio AI interface. And beam prediction has been identified as one use case. So motivated by all these factors, we use LiDAR as the sensing modality in this work, which also provide detailed but privacy preserved data. So we consider an infrastructure mounted LiDAR system following our previous works also for beam prediction assisting a 5G new radio system. We try to focus on predicting the future downlink beams while reducing the frequency of this periodic beam measurement reports, which will result in less resource usage. So our system model, we consider an indoor hotspot scenario with low mobility. There is one access point which is serving in millimeter wave or terahertz. So the idea is we have beam-based connections and the users are assumed to be moving or static inside the area, and the users have UE which is a single antenna UE, and there is a coexisting LiDAR system with two sensors deployed which are working at 20 Hz, and these LiDAR point clouds are used to detect and track the users, and this user trajectory history and the beam sequence history from the 5G system are used jointly to predict the next beam for each user. So our solution consists of these stages. We use the sensing data from the LiDAR sensors, and we do the human detection and tracking, which is done using an adapted method proposed in this reference number 7, which has been used in our previous works also. And then we build a trajectory history for each user, and also we build a beam history based on the beam decision from the 5G system, and we use both of this data as an input to a machine learning model, which is based on a recurrent neural network, and this gives us future predicted beams. Next, we focus on this machine learning model. We have location data in our trajectory history that we build, and it has been shown that classical neural networks such as MLP or fully connected layers, they do not learn successfully features like the location data as they are. So coordinate-based neural networks with the objective to learn a mapping starting from a very low dimensional space like the location data we have. This has been improved with a technique called random Fourier features. So RFF or random Fourier features is a fixed layer which is expressed by this equation, which takes the location data that we have as a sequence, and we multiply that with the R dimensional random matrix, which is the values of the matrix are randomly drawn from this normal distribution, and the variance parameter controls the frequency range that we capture. So the machine learning model that we propose is summarized in this. The objective of the machine learning model is, given a trajectory history and a beam sequence for an observation window, to predict the next beam. So we explored different options for this RNN layer here, and so here we encode the trajectory history with random Fourier features and encode the beam history with one-hot encoding, and then we concatenate the encoded beam and trajectory history with W columns for W time instances inside the observation window, and then we send this into the RNN cell. So within the recurrent neural network, it processes this time series data, and then the output is sent to a fully connected layer, which outputs softmax values, and this the highest value we get out as an output from this layer is considered the argument of that is the next predicted beam. As I explained before, we used multiple models for evaluation for the RNN cell and different target combinations. So we have three models here. First one, all the first three uses RFF for location embedding, and the last one uses multi-layer perceptron. And then for the RNN cell, we use GRU, LSTM, and removed the RNN cell and just replace that with a similar classical layer just to see how it performs. And also the last model has again an LSTM layer. So the performance, if we see about the results, so RFF plus LSTM model performs the best, and as we can also clearly see that all the models that has an RNN cell to process the time series data performs better than this when we have a multi-layer perceptron. And here RFF or multi-layer perceptron for location embedding, clearly it doesn't give much advantage when we see just the top K predictions. But we will later see that when we depend more on the location data, the importance of the RFF layer becomes evident. And one other thing to note is like here RFF plus GRU has the least parameter count. So now we have a ML model which can predict the next beam given the trajectory and beam history. We have multiple options for that, but we have a good model. And then recall that our main objective was to reduce the frequent measurement based beam selection or beam measurement reports. So what we do is we increase the interval between these periodic beam reports and utilize the predicted beam from our machine learning model. The model also outputs a confidence score from the softmax layer. We use this confidence score to measure whether how confident is the model on the beam prediction, and based on a threshold we trigger an aperiodic CSIR S beam report if the confidence score is less than the threshold. Here this beam measurement report is requested for the top gauge beams whose sum of the confidences score satisfy the threshold value. Here we present the top 1 accuracy for the different models with the increasing beam reporting periodicity. And here we have considered only the RNN models, which we identified that it is needed. So and also we have evaluated a beam only model which doesn't use any location data, just beam reports to compare, and we can clearly see when the periodicity is increasing, the RFF equipped layers, the models, they are performing better compared to the other two models. So we can clearly see that the RFF layer is important in the location embedding, and GRU or LSTM, they equally perform better. LSTM is slightly better, but given the parameter count is less, so we chose RFF plus GRU model as our final model. So this shows the variation of the top band accuracy with the effect of the threshold for the RFF plus GRU model that we earlier chose. And as you can clearly see now, if the number of if the threshold is very high, the number of aperiodic CSIRs we trigger are high, which gives us a good accuracy because it's always refined from the beam distance from the 5G system. But the global trend is when the reporting periodicity is increased, the accuracy goes down. But still, our model with the thresholds can maintain a good accuracy. If there is no aperiodic CSIRS, there's a significant degradation. So use of aperiodic CSIRS improves the accuracy. This shows the resource usage of the CSIRS beam reports, the effect of the threshold, and as I said earlier also, when the threshold is higher, we trigger more and more aperiodic CSIRS, which uses higher number of resources when we compare to no aperiodic CSIRS case. And if you think about increasing the periodicity up to 10, we can save 90% of the resources with no aperiodic CSIRS case. But if we just use some amount of aperiodic CSIRS to improve the accuracy, we have to pay a bit more of the resources. And for this scenario, we chose 0.85 as a good threshold because it gives good accuracy as well as uses a less amount of resources. Here we show the performance of the beam prediction in the time as an example for a user 2 in the scene 4 that we use, and the interval between 120 and 190 time instances. So the periodicity is at 10 and the threshold is set to 0.85. As you can see, we can achieve almost optimal beam SNR, and here it shows the beam change differences in indexes, and here the highest layer shows the aperiodic CSIRS beams used, and we can see these are the predictions. So here we save the periodic beam measurement reports, and this gives us like increased periodicity of 10, so periodic beam measurement reports. And this shows the confidence score. As you can see, when the confidence score goes below this threshold, an aperiodic CSIRS is triggered. So this area, there are a lot of aperiodic CSIRS triggered because it's a beam transition area. So in other words, this method also identifies beam transitions correctly. So it also has that effect. So as the conclusion, we proposed a method for beam prediction for a 5G NR UE based on a coexisting infrastructure mounted LiDAR system. The system utilizes LiDAR data to track, detect and track the users, and then use the beam decisions from 5G and location history to predict the future beam indexes. So this predictive beam management method that we propose with the thresholding and the confidence and using aperiodic CSIRS, it demonstrated that it achieves an acceptable accuracy while saving a significant number of resources. So this shows that we can use such a system, a LiDAR system with the network, and it can be useful to enable efficient beam-based operations. And however, we know these are uh, uh, basic simulations, so a more comprehensive system-specific study with dynamic simulations are needed to identify the true gains, which will be done in the future. So these are the references that I have used, and there are more in the paper. So thank you. And if you have any questions, you can send me an email to this email address.